Hello, this is Josh Cortez. This is my submission video for CSC412 Project 4. So we did classification and regression, and yeah, we just get right into it. So here we have the mounting of the cell. In this cell, we have the mounting for our Google Drive. These both of these are just our setups. So they mount my Google Drive and copy the CSV file and the helper script into the working folder. Nothing interesting. It's just it's fine. Okay. And here I have the imports for pandas, NumPy, Matplot, Seaborn, and all the six SK learning models. So the last line here loads the heart underscore disease CSV. So that's just our data. The output confirms the shape. So it is 1,025 rows by 14 columns. And I got this data from Kegels. I got it from both of these CSV files. And for this df.head, the first five patients, so you can see the 13 input features like age, sex, CP, trest BPS, which is just the resting blood pressure, and col for cholesterol, and phallic, which is the maximum heart rate, and so on. As you can see, all these different columns. The last column there is target. A 0 is meaning no disease, and 1 means disease. And in this df underscore dot describe, just the quick summary stats. So ages range from 29 to 77, cholesterol from 126 to 546, nothing unusual, and there's nothing really that we need to check out here. And on this class distribution check, the cell checks the class balance and missing values. So classes are 526 with disease versus 149 without it. Yeah, that's pretty much it for that one. And 0 missing values, so I don't have to clean anything up. And now for some visualization. On the left, the class balance is a bar chart. So and then on the right is a heat map of how each feature correlates with the target. The strongest signals are chest pain type, max heart rate, and slope. Cholesterol is a pretty weaker predictor, surprising, but that's what the data shows. And for the pre-processing, so the label encoder on the target column, since the target is already 0 and 1, nothing actually changes, but I left it in to match the tutorial from the demo. And for this filtered data, I separate X from X is all. I separate the data, so X is all 13 input features, and Y is the target column. The output confirms here that it is 1,025 and 13 features going into X. And for the split into training and testing, so the train test split is at 80-20 with random state equal to 42. So that gives me 82 training samples and 205 testing samples. And here we have our models. So for the 6 models that we have, the 4 of them from the class or demo was the KNN with 5 neighbors, so it classifies the majority vote of the 5 closest patients. The decision tree, which is a flow chart of yes or no questions. Naive Bayes uses probability, assuming features are independent. SVM and RBF kernel, which draws curved boundaries between classes. And the 2 ones that I added are random forest, which is 100 decision trees voting together. I picked it because it extends decision tree and reduces overfitting, as well as gradient boosting. So trees built one after another, each fixing the last one's mistakes. So usually the strongest in tabular data. And down here we have the accuracy bar chart. So these are just all the accuracies side by side. KNN we have at 73.2, decision tree at 98.5, 80% for naive Bayes, SVM at 68, or 0.3, sorry, random forest at 98.5, and gradient boosting at 93.2. And down here we have the confusion matrices. So the 6 confusion matrices per model, or I'm sorry, there are 6 confusion matrices per model. So the top left and bottom right squares here, um, these are the correct positions. The other two are errors. Decision trees and random forests only miss about 3 out of 25, or 205, I'm sorry. And the SVM has a lot of errors. So if I can show you here all of them, we'll just go slowly. So yep, this KNNN, decision tree, naive Bayes, SVM, random forest. Oh, whoa, it like snaps down, and gradient boosting. And here we just have the classification reports, so shows precision, recall, and F1 score for each class, as well as the decision tree and random forest both hit 0.99 across the board, and SVM sits at around 6.68 to 71. So here they are. And I will cut it, and I will see you guys on the next regression, or on regression. Alright, so here we are for the regression. Again, these are pretty much the same thing, except for the fact that it's a different CSV file because we have different data. And yeah, so this is our mounting, and then connecting, and then our imports again. This is the exact same as up here, or up here, just changes for this class, or this regression model. Or not model, I guess, but just regression. And down here you can see for the final output, or the imports and loading the California housing file, output shows it's pretty big compared to the heart diseases one, but it's around 20,000, or not around, but it is 20,640 rows and 10 columns. And let's go ahead and go down to df.head. So the first 5 rows, each row is a California neighborhood. You can see the 9 features: longitude, latitude, house median age, total rooms, total bedrooms, populations, households, median income, and a text feature called ocean proximity there. Values like near bay, inland. Last column is the median house value, or second to last, I'm sorry. Median house value. This is what I am predicting. So down here on the df.describe, summary stats. This is the same thing as before. So well, it does the same thing as before, but obviously the output will be different. So notice how the median house value goes up from about 15,000 all the way up to 501,000. The max actually is a hard cap in the data set, and it'll come back to matter later. And here for the visualized data, on the left is a histogram of the target. Prices are right skewed, and you can see that the tall bar at the end, that is all the houses capped at 500,001. On the right is the correlations with the target. So median income is by far the strongest predictor at about 0.69. And for the pre-processing here, let's go down. So 2 steps here. First, I drop the 207 rows with the missing bedrooms. That leaves 20,433 rows. Excuse me. Then the label encoder on proximity, ocean proximity, to turn each text category into an integer. So less than h1 ocean becomes 0, and inland becomes 1, and so on. And here on the filtered data, we separate the X, which is the 9 features, and Y, the house value. Output confirms 9 features going into X. And for the testing and training, it's again an 80-20 split with random state 42. That gives me 16,346 training rows and 4,087 test rows. And for the scale feature, the standard scale on the features, this is important for linear regression, which is sensitive to feature scale. Random forest doesn't really care about scaling from earlier, but it'll use the raw data for that one and scale data for the regression, or linear regression, I'm sorry. And here we have the 2 models. So linear regression fits a straight line. I plain baseline, no tuning on purpose, and so I can see how much of the price is just a linear relationship. And then the random forest regressor, it's 100 trees averaged instead of voting. I picked it because the housing prices have linear patterns, location effects especially, so that straight line can't just capture those things. And the output prints, let's see. Oh, there you go. It's at the bottom there. So the output prints the R squared, the RMSE, and the MAE for both. You can see that the random forest beating linear regression on pretty much every metric. So here for the metrics tables, or table, sorry, a clean side-by-side comparison. So, oh, got that again. Oh no. There you go. So linear regression has R squared of 0.64. RMSE is around $70,000. MAE is around $51,000, and the random forest is at a R squared of 0.282, RMSE around $49,000, and MAE around $32,000. And random forest cut the average error by about 20,000 and explained 18 more points of variance. So looking at those bar charts, some numbers visually on the left, or same numbers visually, I'm sorry, on the left R squared, higher is better, and random forest wins on that. And then on the right, RMSE, lower is better here, and again, random forest wins again. So down here at the actual versus predicted, the scatter plot, each dot is one neighborhood, and the red dashed line is a perfect prediction. So linear regression points spread wide around it, and the random forest pretty much random forest points hug it much tighter. That horizontal line of dots at 500,000 in both plots isn't a model bug. It is this the data set price cap stopping us there, or just taking us down on that one.